In this video, I'm going to show you how to modify engineering software for your own purposes. So for some context, when you take my course, for the first 4 weeks, you're learning the Python basics through the creation of your first engineering toolkit module called beams.py. In beams.py, you learn how to read a text file which describes an arbitrary beam with arbitrary loading. You send that data over to some structured data format, and then you send that data into an API for processing. So in this video, I'm going to show you 5 modifications that I've made to my own beams.py module to add some extra features that makes it particularly nice to use for production engineering work. This is structural Python. So here is what one of these beam files that we use looks like. We've got the name of the beam, and then we've got a row of numbers here. These numbers represent the length of the beam, the elastic modulus, the moment of inertia about the strong axis, moment of inertia about the weak axis, the cross-sectional area, and the polar moment of inertia. We've got the next line representing the supports on the beam. So we've got a pin support at 2200 and a roller support at 6600. The remainder of the file describes the loading on the beam. So for a distributed load, we have it happening in the Fy or gravity direction. This is a magnitude of -30 at the beginning of the load, -30 at the end of the load, starts at the position 0 on the beam, and goes to 8800 and is the dead load case. So you can see how the live load, snow load, and then an additional point load in the dead and point load in the snow is added. The idea with this beam file is that it takes a lot less time to write one of these than it does to, say, load up a large analysis program and set up all of your load combinations, your load cases, your grid system, and then your sections in your database, and then drawing the actual beam, then assigning all the loading to it. That'll probably take you about 10 or 15 minutes. So by writing a quick text file like this, we not only have a quick way of creating a beam, but we have a way of now storing the information about the design that we used. And we can actually put this into a version control system so that as things change, we can track all changes. A very powerful tool. So here's what it looks like under the hood. So we just start off by reading a beam file. Read the text and the data. It just returns us a list of text. We then go through each of the parts, the beam attributes, and we parse it, meaning we make some meaning out of it by putting it into some structured data format. We parse the supports. We convert things to numeric. We parse the loads. We then get the structured beam data, which is where we do all of that parsing work. And at the end of it, we get this nicely organized, what's called a dictionary. That way, when we send it to the build beam function to build our finite element model, everything's nicely organized and we just plug all the pieces together. So how does that actually work? Well, if we've got our beam file here, gb1.txt, we just go ahead and read the file in using the read CSV file, and then we can use get structured beam data to see what the structured beam data looks like. This is an intermediate step here. We normally don't run it, but I want to show you what the intermediate file looks like. So this is what structured beam data looks like. We've got the L, E, I, Z, I, Y, all of the components neatly organized so we can see at any point what each of these numbers represents. But to actually use this, all we have to do is call the function that we've written called load beam model, give it the beam file, and we specify the load combos that we want it to use. That'll give us the finite element model. We then analyze it, and then we can access the member inside. Analysis done. Let's see what it looks like rendered out in 3D. Here's our model here with all of our loads on it according to the, the L2CB, LC2B load combination. So let's get rid of that window, and now we can plot the shear. We can plot the moment. We can plot the deflection for any given load combo that we want. One of the things you might be noticing about this beam file is we've got a bunch of loads here that are described. We can see the dead load and snow case, but we don't know where they're from. I often find it would be so useful in analysis programs to be able to put comments on our loads, kind of like this. So putting a comment onto the load, so that way when we're reading this back and we're trying to understand what we did maybe yesterday or last week, we can see exactly what the loads are coming from, and it sort of makes it a little bit nicer to use. So how do we implement that kind of a feature? Let me swap over from the version that we of the code that we use in the course and to the version of the code where I've added this feature in. And I think I called it comments on loads. So now when I switched the version here in my GitHub desktop, the actual code changes on disk. And now it has the additional functions required to do this. So let's look for comments. Remove comments is the name of the function I wrote. So here's the strategy I took. If I'm reading the raw data file, the content of the comments themselves are not used for the analysis, nor do I need to keep track of them in the structured beam format. All I have to do is just kind of strip them off, and then my beam file operates the exact same as it did before. So here's the approach that I took for this. I decided that I was going to operate on the raw data that comes in after I've read the file. I'm going to do a double loop, looping through every element in every line. And if I find the little comment tag, which is consistent with the Python code, if I use the same symbol in my beam file, if it finds that element in the line, then it just goes ahead and splits the data on one side of the comment. So it splits against this and it keeps all of this on one side, keeps all of this on the other side, and in the process of splitting, it removes this character. So if I remove that character and then get rid of everything on the right-hand side, I've effectively removed the comment. So, and then I'm left with the same format that I originally had. So if I'm left with the same format I originally had, I don't need to change any of my other functions. I just run this file now through the rest of the process and it works just fine. So to show you how that works, let's, instead of reading the gb1.txt, let's read gb1 comments. Now I'm just going to make sure that I've indeed updated my code and I've set auto reload here. So I can change the code on disk and it will be updated in my Jupyter environment instantly. There we go. And let's look at the shear and the moment. It's the exact same still. No change. So that's good. Right now I'm specifying a UDL as a distributed load, right? And so oftentimes though, we don't have a line load coming down directly onto a member. That line load is basically being generated by other framing members coming into it. In other words, we have to do some pre-processing on our own before we can actually set the UDL. So what if we could do that as part of the beam file? So I've created now, instead of dist, which to describe a distributed load, and point to describe a point load, the only two load types I currently have, I added two other load types. Actually, I added three: trib width, trib variable width, and trib area. The idea with the trib width is all I have to do now is set the area load, the width of the trib on that member, and then the start and end location. For the variable width, I set the overall magnitude of the area load, and then I say the trib width at the beginning of the member and the trib width at the end of the member, or rather the trib width at the beginning and the end of the load is, and then the load is applied at this X location and ends at that location. And then with the trib area, it's just the magnitude of the area load times the trib area, and then that gets converted to a point load. So let's go ahead now and see how I implemented this. The idea with this one is I needed to basically do a processing step between the raw data and the creation of the structured beam model. The structured beam model here, with all that dictionary with all the data that's sort of nicely formatted, is where I've got everything ready to go into the analysis program. Now the analysis program doesn't know what a trib width or trib variable width is. It has no idea of that. So in order for it to go into the analysis program, I need to basically convert my raw data into just pure dist loads like this. So let's see what that actually looks like. So I've read the file from the trib loads, and you'll see here that these trib width and trib variable widths get turned into dist loads like that. So here's the variable one. You can see the start and end magnitude, the same start and end location as this guy here. Last one, this trib area gets converted into a point load as well. In the function here called parse loads, I added some additional load types. So this is where I defined what my load types were coming in from the file. So here's what the file looks like. They look like dist point. So I needed some way of recognizing those as these other names came in. So I've got if load equals point, if load equals dist. Then I just created some more clauses. If load type equals trib width, if load type equals trib variable width, and if load type equals trib area. Now I had to do some slight modifications here, and I created this little function called calculate line load from trib width. It takes a magnitude and a width, and it returns to me the UDL start and the UDL end. I did the same thing here with calculate line load from trib width. In this case, now I passed it width start and width end, and it just calculated line start and line end for me. All of the other data is the same, and then I could just plug that in right into my structured data. With trib area, I've got a similar situation where I've got this little helper function called calculate point load from trib area. It takes an area load and a trib area, basically just multiplies them together. But instead of me multiplying them here, that's sort of like a different concern. I wanted to have the ability to have the actual calculations done separate from the parsing of the data. So that's why I created a little helper function to do that on the side. Then I just use the trib area one to create a point load. And then I just pass in the direction, the magnitude, which has been calculated from the little function here. The area load and the trib area are used to calculate the magnitude, but then the location is just in the file itself. So I just plug that in. Same with the load case. So we can run it and we can see the shear and moment and deflection just the same. So one of the things that I found with this beam file format is you have to know in advance what these numbers here in the beam definition represent. You have to know that the first number is the length, the second number is the elastic modulus of the material you intend to use. The third number is moment of inertia about the strong axis, moment of inertia about the weak, area, polar moment of inertia. So it would be a lot nicer though if they were like, sort of like keywords that we could put in here, or keyword arguments in Python, like this. So I could say length, elastic modulus, and I could choose to use them or not. And then I could say IX, IY, AJ, something like that. So now somebody reading this can understand exactly what each of these means. Now I set it up so that I could choose to put in some of these keyword arguments or all of them, but just like Python syntax, I set it up such that if you start off using just the positions, like positional keywords here, positional arguments rather, and then you switch to using the keywords, you have to keep using them the rest of the way. I can't like do this. This will cause an error. And in fact, I set up an error checking to make sure that I caught that. So length, E, IX, IY, AJ. Now the Pinite program, they calls the strong moment of inertia IZ. Now, some programs use IX for the strong, some use IZ, but all of them use IY as the weak axis. So I set this up so I could either say IX or IZ if I didn't remember exactly how Pinite worked, or if somebody else was using this, they weren't really sure sort of which one's which. So what I need to do is I need to handle this part of it in the part of the process where after I read the raw data, and I'm parsing the beam attributes. So I need to add some additional steps into that function, parse beam attributes, to make this work. So what I had to do is I had to do multiple loops here to basically go through all of them, see if there's an equal sign, and if it's a string, and if it is, then I sort of take the left-hand side and the right-hand side and put it into a dictionary of arguments. And if it doesn't have an equal sign in it, then I just take it, the value as it is, and I assume it's the first argument in the order of arguments. And if there's not equal signs in there, the rest of them, then it raises this value error saying beam file cannot have positional beam attributes following keyword attributes. So then I go through here and I go through all of the ones remaining, and now that they all have equal signs in them, I just split them up, get rid of any sort of spaces around them, and then just add that to my dictionary. And so I've got my parsed positional args, which is the ones that didn't have, an equal sign beside it. And I've got my keyword args here, and I join them together using the pipe operator between dictionaries here. The build beam function expects them to look like this: capital L, capital E, I, Z, I, Y, A, J. And so these are the values that I accept in replacement of. And when it runs through and checks to see which ones that I've used, if it finds lowercase e, it replaces it with uppercase e. Finds IX, it replaces it with IZ. IX lower, then it replaces it with IZ. Anything that's been read in replaces all of the default values here. And if there's a key in the default attrs that's not in the beam attrs, then that key in the default attrs will remain as 1. Let's go in and see it work. And so we can look at the structured beam data here to validate that what we are getting is what we expect. And so the other thing is, if I actually remove this here and save it, I should see that error come up because I'm trying to switch from positional arguments to keyword arguments and back to positional. And here's the error we see here. We've got value error, beam file cannot have positional attributes following keyword attributes. So now we can put that J argument back, save it, and we can see that value error go away. And then we can run the beam file and look at our shear. Just the same again. Okay, the next modification I want to show you is the big one. This didn't take 10 minutes. It probably took maybe about an hour and a half. So the idea here is to be able to replace any of these values with, say, a unit like that. So instead of -84 and just being sort of some unitless thing, then I also can specify, say, -84 PSF, or I could say or I could say 4.8 KPA, like that, and have everything just work. And the person who's reading it can just see that, oh, they're using KPA, and it's unclear whether this is millimeters or meters, so you could use millimeters here like that, and just have all these units get parsed, and then to use my library for all people to actually handle all the unit conversion. And so in order to make this work, I have to be able to, one, have some default unit system. So if I were working in SI units, then it would be sort of newtons and millimeters. If I were working in, say, US units, it might be pounds and inches. And I need to be able to take units from a variety of systems and convert them all down into floats that represent units in that system. So what's the idea here of how to do that? Well, it occurred to me that I need to establish some sort of base system. So I decided here to put sort of a scaling system here that I'm going to be using at the bottom of the text file. Why at the bottom? Well, I figured that the top of the text file is already sort of spoken for. I've got the name of the file there. The second line is always going to be the beam attributes, and I wanted to kind of keep as much of my code unchanged as possible. The next line is the supports. So if I put anything in here, I'd be changing sort of the order of all the stuff getting parsed. Then I've got loads. So the idea is that it's name, attributes, supports, and everything else is loads. So if I put it at the end of the loads though, then I can always just go to the end of the file, get that data out and sort of extract it, remove it from the data in the file. And then once I've read it, I can toss it away. And now the rest of the file is exactly the same as it was. So it's one small change, and it seemed like a good place to put it. So now you can see here where it says units MPA. I decided here to I was trying to find a concise way of describing the unit system. And so instead of saying like n comma millimeter for like newtons and millimeters as the convention, I decided instead to use the units of stress to describe sort of what everything is using in the grand scheme. So MPA is commonly described as newtons per millimeter squared. So using MPA implies newtons per millimeter squared. And so if I used KPA, it's commonly referred to as kilonewtons per meter squared. So that's kilonewtons and meters. And I use GPA, that's kilonewtons per millimeter squared. So that implies kilonewtons and millimeters as my sort of unit scaling. So how can I go about adding all of this capability with changing as little of my code as possible? Well, we've got this beams.py file here. Let's switch over to the units version of the code. So let's see how I did this. Instead of putting everything in beams.py, because I realized that handling units like this from strings, like parsing unit data from strings, is not something that's specific to my beams.py file. I might want to use the same capability in other situations in my engineering toolkit. So I put all of this unit stuff in my utils file, which is where I've got my, say, text to integer conversion and text to floating point number conversion. I decided to put all my unit stuff in there. So here's a quick scroll through it. I've got the function parse unit system, the function parse unit string, parse exponent, parse architectural notation, because maybe I wanted to have things, I could say 1 foot 6 inches by saying 1'6 or 0'4 space 5/8 to mean 4.65 inch. I wanted to have that kind of flexibility because when I'm working in US units, that's kind of the conventional way to describe lengths. So I wanted to be able to parse the architectural notations. And then I wrote this one function that's called convert unit string that does all the other stuff. It parses the architectural notation, it parses the unit string, gets the quantity type, meaning whether it's like a force or a length. And then I've set up this big series of if and elif statements to handle the conversion of all the different possible unit types that I could be handling in my sort of structural analysis tools. So I set up this big long if statement to do that. And then I also created this little helper function here to help me determine what I'm looking at. Am I looking at a length, force, pressure, line, or moment? Now, because I'm writing my beam files, I get to choose how I want to write stuff. And I didn't feel like doing sort of like unit caret exponent like this. I just wanted to be able to say like inch 4 and have that sort of mean inch to the power of 4. Same with this, millimeter 2, millimeter squared, millimeter 4, millimeter to the power of 4. All right, so I've got some units here. Let's go ahead, and I'm in units of MPa. So that means if when I use inches to the 4th, that's going to be converted into millimeters to the 4th. So let's save that and read it in. And let's see what the structured beam data looks like that we get as an output. So 8800, it's in if I don't specify a unit, remember everything's in Newton millimeters. So if I don't specify a unit, it's assumed to be millimeters, assumed to be MPa because it's in the units of MPa. Now look at this one here. This one is in inches to the 4th, and this one was approximately similar to my original value here, 1290 e to the 6th. And so I chose a value that's similar, but you know, still a nice round number. So 1250 e to the 6th millimeters to the 4th. Same with this value, still the same because I'm using millimeters to the 4th. A is the same, millimeters squared, and then J is the same because I didn't specify any value there. Like that. Same with this guy down here, and my area, 4.8 kPa times 10.6 meters squared, and it returns it to a value to me in magnitude of newtons, so 130 kilonewtons, 130,000 newtons. So that's adding the units. So this allows me to use the units that I want to for sections, and then which might be in SI units or inches, and then I get to use either kilonewtons and meters or PSF or maybe even KSF if I had this loads that big in the definition of my loads. It's just sort of an extra bit of convenience, so I don't need to like do these little side calcs in order to create my beam files. All right, the last one I want to show you here is about defining occupancies to use in your project instead of having to define dead, load, snow, wind, load components onto your beam individually. But before I get started, I just want to mention that a large windstorm just rolled in here. So if you hear some wind noise in the background, that's what's going on. We've got now this other idea here now. We've got occupancies. So instead of me now describing, like here, separate load components manually, wouldn't it be much more convenient to just set up certain occupancies and then say the residential occupancy with this trib width, and the residential occupancy might have 1, 2, or 3, say, load components. Instead of me having to manually specify all 2, 3, 4, 5 load components every time that I want to use the residential loading, I instead just define a residential loading in a JSON file, and I store that with my project directory where I've got all my stuff, you know, for the project as a whole. This way it's kind of like note-taking as well. I'm defining what my loads are prior to doing any design work. So now I can just say the residential load, the lower canopy load, and the upper canopy load, I give it a trib width, and then when I read it into the module, it breaks everything out into the structured beam data format before sending it to the analysis program. Let's now swap over to the occupancy loads branch, read the occupancies text file, but now I have to also read the occupancies JSON file as well. So Let's pull this up here and let's add an additional line here with open occupancies.json as JSON file. And then I'll use the JSON module in the standard library to read my occupancy data with json.load JSON file. And that converts everything into a dictionary for me. There's our dictionary, the same as this one here. So now I can pass that occupancy data into my get structured beam data file format. So I'm going to re-import here just to make sure that it's reloaded, because now my signature has changed for this function. It now takes an occupancies in addition to raw data. So occupancies data. Now this occupancy here, the residential, has been broken out into its dead and live components. So it's automatically created a distributed load for the dead and the distributed load for the live, and both of those together represent the occupancy loading. So let's comment this all out and see what it looks like to run the file. Now I need to make sure that I add my occupancies.json file here, and then I can read the file and get my beam model. I can look at the rendering, and now I've got all of my different load components onto my beam. I can see the shear diagram, the moment diagram, and the deflection. The point of this is to create an analysis report. So using the tool that I created in Workbook 6 for the reporting module, I'm going to just pass my analysis model right into the create beam report function. And then now I've got my analysis report. So there, from this file, this occupancy data, I've now created an analysis report with my maxes and mins, with my envelope, and all of my reactions for the different load cases. This is the whole point behind making your engineering toolkit. You build the base functionality, and then you can modify it to suit your purposes. Now, the idea is not to just sort of create a finite element model, is to get an analysis report so you can make decisions about what the design is going to be. So now I'm going from using a very basic tool that uses a lot of this sort of manual entry to now using a very slick and customized tool that allows me to work quickly and efficiently with complicated load types on any kind of beam. This is the big idea here. If you're currently active in my course Python for Structural Engineers, you will have access to all the code behind the scenes to make these modifications possible. But remember, these are just modifications that I made to suit my way of working. You may do it differently for your way of working. Now, if you're not active in my course, Python for Structural Engineers, you can go to structuralpython.com to learn about the next training opportunity and learn how you too can be the conductor of your own engineering orchestra.